Hello there, and welcome back. In this video, we're going to continue our exploration of continuous random variables and probability density functions. Up to this stage, we've discussed three distributions in detail: the uniform, exponential, and the gamma distribution, and we've discussed some applications associated to each of them as well. In this video, we're going to be introducing two new random variables, the normal and the standard normal PDFs. So what is a normal random variable? So we're going to be assuming that x is a continuous random variable on minus infinity to infinity. So just this starting premise is a little bit different from the other three. Remember, uniform was on the interval a to b, exponential was on the interval 0 to infinity, and gamma was on the open interval 0 to infinity. So normal random variables have a broader range of values for which they can take, so it's not bounded above nor below. In order to use the normal random variable in the normal distribution, you need to know the expected value and the variance. Let's call the expected value for this random variable mu. Let's call the variance sigma squared, or the standard deviation just sigma. If this random variable follows this complex looking distribution, so 1 divided by sigma square root of 2 pi times e to the power negative 1/2, all in parentheses, x minus mu over sigma the quantity squared, then x is called a normal random variable whose PDF is this ugly looking thing. So let's just look at a particular example that we can actually just solve using this bit of information that we have so far. So example 1. So let us suppose that the IQ scores for a population are normally distributed with a mean score of 87.3 and a standard deviation of 5.2 IQ points. So if a person is randomly selected, what is the probability that their score, x, is going to be larger than 92? Right? So if you take a look at what this distribution looks like, a normal distribution is actually going to have our little bell-shaped pattern, right? So this is a symmetric distribution around the mean. So our mean is 87.3. So one can show that the area underneath a probability density function, regardless of the mu and standard deviation, is always going to be equal to 1. So what do we want? So we want the area under the curve from 92 to infinity. So this region here is going to give us the answer to this problem. So that means this is going to be equal to the integral from 92 to infinity of our normal distribution function. And once you do this in Desmos, for example, you're going to have that's approximately equal to 0.1830. 0.1830. Right? Now, some people will use, for example, tables. Tables can sort of give you these things if you don't have access to a calculator or Desmos. But as long as you have some ways of evaluating these, because normal distributions do not have an elementary cumulative density function like the exponential function did. So you would have to have a calculator or Desmos in order to calculate this, or some other method to sort of get these areas into this curve. Now, what if we want to solve the problem? What is the probability that a randomly selected person has a IQ score that is less than 85? So remember, the normal distribution is not bounded below, so this is going to be the integral from minus infinity to 85 of our probability density function. And you should be able to find that's going to be approximately equal to 0.3291. So aside from the distribution, there's not really anything new in terms of, what we do in regards to calculating probabilities and so on. The only difference is the shape, right? So what about percentiles? Can we do percentiles with normal distributions? Sure, why not? So remember the cumulative density function. So the cumulative density function, or CDF for short, is not elementary for the normal distribution. But regardless of what it is, if you're hanging out in Desmos, then the cumulative density function can be found by doing the integral from minus infinity to x of our probability density function f. And make sure you use a different variable for the interior. It has to be different. So how would we find the 90th percentile? in Desmos, for example, then you would just, do 0.90 tilde to f of x sub 90, right? So once you type this on a line where all of your density functions and cumulative density functions are defined above, then you're going to find that the 90th percentile is going to be approximately equal to 93.96. So what does this mean? That means 90% of the population, 90% of the population has an IQ score of 93.96 or below, right? So that is the normal distribution, how you can do percentiles with it. Keep in mind the 50th percentile, the median, is going to be the same as the mean because this is a symmetric distribution. Let's look at another question that is actually very commonly asked. So between what two numbers? So between what two numbers is 95% of the IQ scores symmetrically distributed between? So what are we looking for now? So we're looking for two IQ scores such that the IQ score distribution is symmetrically distributed in between each of them. So if we draw our normal distribution, we're going to be looking for two numbers. I'm going to call it XL for a lower bound and XU for an upper bound. And we want to make sure that these distances here are the same exact distance, so the area is symmetrically distributed. And we want this area here to be equal to 0.95. So what are some of the things that we should know? So if 95% of the data is hanging out in the interior, that means 5% of the data is lying on the left and the right tail of the distribution is equally distributed, right? So that means 2.5% of the data is hanging out over here, and 2.5% of the data is hanging out over here, right? So in terms of percentiles, what is XL? Well, XL is precisely going to be equal to the 25th percentile, right? And what about the upper bound? So that's going to be equal to, so we have 95% of the data and 2.5% of the data to the left of it. So that's just going to be the 97.5th percentile, right? So again, in Desmos, once you have all your things, and again, let's assume you have your cumulative density function defined, so minus infinity to x of fx sub t dt, then our lower bound is going to be equal to, so let's see, the 25th percentile. So 0.25 set equal to our cumulative density function, let's call it XL. And our other one, so that's going to be 0.975 tilde fxu. So this is going to give us our lower bound of approximately 77.11 and our upper bound approximately equal to 97.49. And that's how you do percentiles. But this problem is actually going to be very, very useful once we get to confidence intervals a little bit later. But those are some of the basics associated to the normal distribution. Now let's look at a new distribution called the standard normal distribution, which actually makes all these numbers a little bit more nicer to work with. Now that we have some of the basics discussed of the normal distribution, let us take a moment and look at this formula in a little bit of detail. Notice if we look at the quantity that's located inside of our embedded exponent, we have x minus mu divided by sigma. If you remember from earlier on, this is precisely equal to the z-score for a particular x value, which is just a measure of position, right? So this is just particular z of x. Now what we can do is we can let mu be equal to 0 and let sigma be equal to 1. So if we let mu be equal to 0 and sigma be equal to 1, then the z-score for a particular value x is just going to be equal to x, right? So what we are doing here is we're standardizing the probability density function. So when we standardize the density function, also notice that the sigma is also going to turn to 1 as well. Our PDF is going to transform into something a little bit nicer, right? So now we're going to have the probability density function 1 over the square root of 2 pi times e to the minus 1 half x squared. Now this function is actually very, very nice and very useful actually, and it has a very special name. This is known as the standard normal probability density function. So what is so special about the probability density function associated to a standard normal distribution? So again, it's still going to have your bell-shaped symmetric curve, but it's going to be centered at 0, and most of your data is actually going to be hiding between 3 and 4 standard deviations. So if you do the integral from -4 to 4 of your standard normal distribution, you should get something approximately equal to 1. So this is actually very nice, because now we're not working in like the numbers of 90s. If we're working with blood pressure, we're not working in like the 120s and so on. So sometimes calculations can be easily done in the realm of standard normal probability density functions. If you're in one of those classes that are actually working with tables to calculate these areas, then you're actually required to use the standard normal distribution in order to get your answers, right? But if we're working in Desmos, we can actually do most of our problems just with the normal distribution and not have to convert between the two. So what is the standard normal distribution actually represent in terms of applications? So we can actually use that brief observation that we made earlier. So a standard normal random variable describes the distribution not of the values of a data set, but of the z-scores for the values of the data set. Right, so that's pretty interesting. So can we actually solve problems with the standard normal PDF just like we did with the normal? And the answer is of course yes. So for the elementary people, definitely this is the only way that you could go about this if you don't have software. So again, let's assume we're working with IQ scores again, and let's assume our mean is equal to 87.3 and our standard deviation is equal to 5.2. And let's assume that we're interested in finding, well, what is the probability that a randomly selected person has an IQ score between 85 and 92, right? And remember, since we're working in continuous, this is the same as the problem 85 less than x less than 92, right? They are the same thing, different problem though. So how would we, so we can use the normal PDF to solve this, or we could use the standard normal PDF and just look at the z-scores for 85 and 92. So let's take a look at how we would do that if we were actually interested in doing so. So the z-score for 85 is going to be equal to 85 minus the mean all over the standard deviation of the distribution. So that's going to be equal to 85 minus 87.3 all over 5.2, and that's going to be approximately equal to negative 0.44. Similarly, the z-score for 92 is going to be equal to 92 minus the mean all over the standard deviation. And keep in mind, these are values associated with the data set, so z of x values. So that's going to be equal to what? 92 minus 87.3 again, all over 5.2, and that's going to come out to 0.90. So what's the difference or similarities between, using the normal versus the standard normal? So in the normal world, so we're interested in doing, what are we doing? 85 to 92. So we could use either the normal distribution, right, and find this area. So this is the normal PDF. Or we could use the standard normal distribution and go from negative 0.44 to 0.90. Of course, we are rounding, so this area is, of course, going to have some error associated to its calculation, but to some, that's okay, I guess, right? So this distribution is not the normal, but this is the standard normal PDF, right? So in terms of this transformational trick that we're doing, that means the integral from 85 to 92 of fx, where this is the normal PDF, is actually going to be equal to the integral from the z-score of 85 to the z-score of 92 of our standard normal PDF. Right, so this is going to be a different function. So this is my standard normal PDF. And regardless of which integral you use, you should get the same exact answer of 0.4878. Right? Keep in mind, you could be using the cumulative density function for each of these. So if you have your cumulative density function already defined in Desmos, for example, which is the integral from minus infinity to x of f of t dt, then that means the integral from 85 to 92 of your density function can be found by just doing the cumulative density evaluated at 92 minus the cumulative density evaluated at 85, subtracted from each other. You're going to get the same exact thing, right? So let's just do one more little problem on the standard normal, just to sort of see how we would go about solving it. So if x is a normally distributed, what is that letter I've written? Distributed random variable, how many z-scores from the mean will 50% of the data be located? So notice that for this particular problem, notice I'm not actually giving you the mean or the standard deviation of the original normally distributed problem, right? Because I'm not talking about, what are the values that 50% of the data is in between. I'm talking about the z-scores for which the data is in between. So you could be talking about blood pressures, heights, happiness, sleep levels, weights, or pretty much anything. The 50% of the data, if it's normally distributed, will always be located between these two z-scores. And then we would, of course, be able to convert back to our x values once we have our z-score values, but this problem is very powerful in that regard. So again, let's just draw our picture, right? So this is, again, our standard normal PDF. So what do we want? So we want two numbers. Remember, the standard normal is centered around 0, so we're looking for two numbers minus z to z. We don't exactly know what these values are, so we're just going to treat them as unknowns. So we want this area to be equal to 0.50, right? So again, what is this distribution equal to? So this distribution is equal to 1 divided by the square root of 2 pi e to the minus 1/2 x squared. So that's our standard normal distribution. And what do we want? We want to solve the equation. Let's see, what do we want? So I'm going to define a new function g of x. G of x is going to be equal to the integral from minus x to x of fx of t dt, right? So we want this integral to be equal to something, right? So what do we want it to be equal to? We want it to be equal to 0.50, right? So we set that equal to g of z, and that's going to give us a z value of 0.6745. Right? So in terms of Desmos, that would be your line 1, that would be your line 2, and that would be your line 3. And I guess that would be your line 4 output if it doesn't tell you directly. So that means in between the z-scores of negative 0.6745 and 0.6745, 50% of the data will always be between these particular two values. Now let us look at one last example just to close all this off, to sort of see how we can use this information to solve a particular real-world problem. So let us assume that the sleep time of college students is normally distributed with an average sleep time of 6.2 hours and a standard deviation of 1.1 hour. Then 95% of students are sleeping between what two symmetric sleep time values? So again, you could solve this using the percentile approach that we discussed earlier, or you can use the z-score approach. And if you're not using software, then the z-score approach would happen to be the more required version anyway. But regardless of which approach you use, you should get the same exact answer. So let's just draw a picture and sort of see what we're looking at here. Right? So what we're trying to look for is two sleep values. So keep in mind here, the mean of this not really graphed normal distribution is something like this, right? And we're looking for two values such that the area between these two values is 95%. So we're looking for an x value in the lower spectrum and an x value in the upper spectrum. So what are these two values equal to? So equivalently, we can transfer this into the standard normal distribution world, right? So it looks a little bit more normal, right? So if we transform this into the standard normal world, so 0 will be in between, and we're going to be looking for two values minus z and z. And remember, these two values are going to be the same value, just opposites of each other, right? So we can find these two z-scores and then come back and translate into the x value world that we came from. So again, how do we do that? So we're going to be defining our density function, which is 1 divided by the square root of 2 pi, e to the minus 1/2 x squared. And then we're going to be defining a new function, g of x, to be equal to the integral from minus x to x of f of t dt, right? So this is going to be representing that particular region. So what do we want? So we want that number such that that area is equal to 95%, and let's call that number z. So once we have that, we should get a z value associated to our upper spectrum. The negative is just going to be the opposite, but that's going to be approximately equal to 1.95996. So once we have a z-score, how are we going to go back to the original x values that we came from? So remember that the z value for a particular x value is going to be equal to x minus the mean of that value all over the standard deviations of that value. So if I solve this equation for x, because we already know what z is, we already know what sigma is, we already know what mu is. So if we solve this equation for mu, we're going to have x is equal to the mean of the x value plus the z-score for that particular value times the standard deviation associated to that x value. Now this equation, very, very important. So once we have that, since we have our z-score, that means the x value is going to be equal to the mean value plus or minus this z-score we have, 1.95996, times the standard deviation for our data set. So remember, mu was already given. Mu was equal to 6.2, and sigma was equal to 1.1, both in hours. So that means this is going to be in hours as well. So once I do that, my lower bound is going to be equal to my mean value, 6.2 minus, so this is the negative z-score, times 1.1, and the upper bound is going to be equal to 6.2, and the upper positive z-score, 1.95996 times 1.1. And then once you work out those things, you're going to get approximately equal to 4.04 hours and 8.36 hours. So that means 95% of all students are sleeping anywhere from 4.04 to 8.36 hours on a randomly selected day, assuming that each day is independent of each other and they are normally distributed with the same mean and standard deviation each day. So that is just a basic introduction to the normal and standard normal probability density functions, and also how you can implement some of these things in Desmos. But keep in mind, if you have the table, there are several different tables. You need to make sure that you're looking at the right picture, but I recommend the cumulative density perspective where it goes from minus infinity up to some number. But make sure you learn how to use your particular table in case you are in that particular world. But if you're using Desmos or any other software, this is all you need. Anyway, I hope you enjoyed this introduction to normal random variables, and I'll see you in the next video. Take care.
You